So we are doing it. We are coding recursive code. Let's do it some more. I'm going to now be coding another very common example of recursive coding, Fibonacci numbers. Fibonacci numbers are also cool because I can use them to introduce a new complexity class. We'll see in a second that computing Fibonacci numbers using recursive programming is slow, very, very, very slow. Actually, to the n, exponentially slow, as you will see in a second. But let's begin by defining what the Fibonacci numbers and the Fibonacci sequence is. Well, these appear in some curious instances in nature and in other mathematical formula, and can be defined basically by this. The first Fibonacci number, which is usually noted f of 0, is 1. We define it in this way. And the second Fibonacci number, which is noted f of 1, so Fibonacci number in position 0 and in position 1 is also 1. And from here, I just defined the nth Fibonacci number as the sum of the previous two. So if f of 0 is 1 and f of 1 is 1, what is f of 2? Well, it's 1 plus 1, which is 2. And if f of 2 is 2 and f of 1 is 1, it means that f of 3 is 2 plus 1 is 3, and so on and so forth. 2 plus 3 is 5, 5 plus 3 is 8, 8 plus 5 is 13, 21, 34, 55. As I wrote here, you get the idea. Pretty simple way to define the numbers, and it's defined using a recursion itself. So this is going to be easy to code in recursive programming because I have a recursive definition itself here, and this is going to give me automatically my recursive case. So I define a function that I will call Fibonacci of n. So I will compute the nth Fibonacci number, and my recursive call comes automatically given by the definition. So for any given n, I return Fibonacci of n minus 1 plus Fibonacci of n minus 2. As you know, I also need a base case, and I have defined here that when n equals 1 or 2, so I have changed this a little bit, the names, but in the first two cases, I return 1. And that's pretty much it. That's a function that computes the Fibonacci numbers. And let's check if it works or not by computing Fibonacci numbers 1st, 4th, 5th, 10th, and 20th. Does it work? Yes, it does. Okay, so I have computed the 1st, the 4th, which you can see here, and the 10th is 55, which you had also computed before, and the 20th happens to be 6,765, which you can check yourself. Function works. Job well done. We have computed Fibonacci numbers using a simple recursive function. You can see here that differently from before, this function has two calls. Not one call, but more than one recursive call. It has two calls inside of my recursive case. This happens. Sometimes I might even have more, 3, 4, whatever. Okay, I have at least one call to the same function, but I might have more than one. And in all of them, I have parameters that diminish, that go towards a base case, which is also composite. I might end up with 1 or with n equals 2, and they both return 1. So the condition of the base case here is a little bit more complex than before, and the calls are a little bit more complex, and the combination of the results of the calls to make the result of my current function is simpler than before. I just add them up because of how the Fibonacci sequence is defined. So I have my second example of a recursive function. I usually tell you to play with the code as much as you want to, but we are getting into examining the complexity of the Fibonacci code, of this Fibonacci recursive code, and you will see that this one is a little bit tricky because, as I said before, the complexity of this is very high. So for example, let's compute Fibonacci of 40, and as you can see, it's taking a while. Okay, and it's done, but it did take a while. The time it takes to compute Fibonacci numbers grows very fast, and the function becomes very, very slow very rapidly. So let's check this. Let's plot Fibonacci numbers up to 40, okay? And I'm going to compare the time it takes me to compute the Fibonacci numbers up to n with the sum of the n numbers that I saw before. That was, do you remember? It was linear. So I'm going to compute to plot the time that it takes to compute something that's linear and compare it to the time it takes to compute these Fibonacci numbers. Okay, and I'm going to do as usual and plot first the sum of the n first numbers, and this should be linear, but because it's very small, because I cannot compute Fibonacci numbers to up to a very high number, this looks a bit weird, but this is linear. Fibonacci numbers grow very fast, as you can see. When I'm in Fibonacci 40, I'm already at something like 3.5 seconds to compute it. And when I compare them, I can see the difference. The sum code, which is actually linear, looks constant by comparison, looks flat. It's not flat, it's linear. But because the Fibonacci time takes so long to compute and grows so rapidly, it appears constant, it appears flat. Okay, remember that plotting the time gives me some interesting intuitions, gives me some comparison, but it's not perfect. It has its limitation. If I only looked at this, I might think that this is constant. It's not, it's linear. But the important thing here is that this is very, very, very slow. How slow is it? Well, let's follow the trace of execution, which in the case of recursive functions means that I start with one function and consider the recursive calls. I start with Fibonacci of n, and what happens? I make two calls, Fibonacci of n minus 1 and Fibonacci of n minus 2. Each of these creates two calls. Fibonacci of n minus 1 creates Fibonacci of n minus 2 and Fibonacci of n minus 3. And Fibonacci of n minus 2, the second one, creates Fibonacci of n minus 3 and Fibonacci of n minus 4. And you can see that I'm starting to see repetitions here. And then I would go on and on. Fibonacci of n minus 2 creates again Fibonacci of n minus 3 and n minus 4. And Fibonacci of n minus 3 creates Fibonacci of n minus 4 and Fibonacci of n minus 5. And on and on and on. And I can get a nice visualization of the recursive tree of calls using a tool by someone called Bruno Papas, who very kindly made it publicly available online, and I encourage you to check it. But if I called Fibonacci of 10, then I would get this super huge tree of recursive calls, okay? I would get first 10, and this would call Fibonacci of 9 and of 8, and each would call number of calls, and I would end up with this tree. Given that everything inside of the function, let's go back to the function. Given that everything inside of the function is constant, okay, I have a comparison here, another comparison, a logical operator or an if, all of these things are constant, and return, which is constant, and then I have two calls. So basically I have functions that are constant, and I have many of them. How many of them? This many of them. Okay, so the number of function is what determines my asymptotic cost, my computation time in this case. Okay, how many calls do I have for a given value of n? Well, as you can see, this is a binary tree. It's divided in two at every node because of the 2 calls that I have for every call, 1 and 2. This gives me this binary tree, which has height, see, this starts with 10, which would be n, 10 minus 1 and minus 1, so on and so forth until I reach 1. Okay? So the height of this tree is n. It's n minus 1 actually, but for an additive constant it's n. Okay? So the size of the whole tree, binary tree of height n minus 1, okay, could be up to 2 to the n divided by 2. Basically, I can double the number of elements at each level. So I have 1, 2 to the 2, so 4, which is 2 to the 2, 8, which is 2 to the 3, and so on and so forth, up to 2 to the n minus 1. Okay, so after expressing it like this, 2 to the n minus 1 is the same as 2 to the n divided by 2, which is 1/2 multiplicative constant. I can say that the number of calls, and because of it, the cost, the asymptotic cost of these algorithms is of the order big O of 2 to the n. So this is exponential cost. I have seen an exponential cost algorithm, and that's why this was so big, why this grew so big, because instead of having something like a linear function, I now have an exponential function governing the behavior of the computation time of my algorithm, how the computation time of my algorithm grows when n grows. In this case, the computation time of my algorithm grows exponentially when n grows. So I have a new complexity class, one that's much, much slower than anything that I had seen before. So far I saw constant, which was the fastest because it didn't grow, linear, which grew following a line, quadratic, which grew following a squared function, and now I have seen the exponential. Okay, this is not n to the 2, this is 2 to the n, which is much, much, much faster growing. These algorithms are much slower. They take a lot longer than any algorithm that we had seen before. Just a quick word to wrap up this part. Those with a more mathematical inclination might have noticed that this tree might have 2 to the n minus 1 nodes, but it doesn't. It's not full. Okay? So what I am saying here is not completely and actually true, and it's not. You can check that the actual number of nodes is not 2 to the n minus 1, but it's phi to the n, where phi is the golden ratio. This requires a bit more deep mathematical demonstration. I hope that you will agree with me that this is smaller than 2 to the n, but it's around 2 to the n, and around means that it's actually phi to the n. Phi is 1.71 something, and I can turn one into the other using multiplicative functions. So all the classes that are a to the n, where a is something bigger than 1, are considered exponential growth functions and follow a similar path. Okay, I spoke and named it 2 to the n for ease of explanation, and if I want it to be very, very detailed, I should call it phi to the n. Everything stands. Phi to the n is very slow, as 2 to the n is, okay, but I would have had to give the very detailed mathematical demonstration, which you can find in the link, but I'm not going to stop at it now. To finish with the Fibonacci numbers, is this algorithm optimal? Can I do better than 2 to the n or phi to the n? Well, yes, we can. Let's consider an iterative version of Fibonacci. So our problem is that we want to compute the nth Fibonacci number, and our first strategy was to use an exponential time recursive algorithm, which was very slow. What happens if I just do a simple loop? Iterative Fibonacci of n basically appends to the list that starts with the first two Fibonacci numbers the number that's made by adding up the two previous numbers in the list. Okay, and I can compute this, and as you can see, I can compute the Fibonacci numbers up to 1,000 pretty fast. Okay, and they get very long very fast. What is the complexity of iterative Fibonacci? I leave it as an exercise for you, but you can follow the trace of execution and see what happens here. It should not be difficult for you to check that this is much faster than the recursive version that we did before. So to answer the question, is the recursive algorithm optimal? It is not, because this other algorithm that solves the same problem is much faster. You can see that it has lower complexity, and then you can even ask yourself whether or not this one is optimal. Spoiler alert, it is.